we're gonna open up the setup, turn on double precision, and set the solver processes to 4. We'll click start. I like to work from the top to bottom, so we'll open up models. And anytime you're working with heat transfer, you want to turn on the energy equation. We'll double click viscous and set our parameter to K epsilon, realizable, and enhanced wall treatment. So now we're going to open up the materials. We'll double click air, and to add materials to this simulation, we'll click Fluent Database, scroll all the way down, and we'll add liquid water. This is going to be the cold water on the shell side. We're also going to add water vapor. This message popped up because I had water, liquid and water vapor selected when I went to copy, but we already had liquid added already. So in the tree, you can see that now we have the liquid water and the water vapor. So now we're gonna open up the solid. And so for all the metal for the heat exchanger, we're gonna open up Fluent Database again. We're gonna change the material type to solid. We'll select steel. Close that out. So we're done with the materials. Now we're gonna open up the cell zone conditions for the fluids. Double click the cold domain. We're going to change this material to the liquid water. And in the concentric tube, which is our hot domain, we'll add the steam or the water vapor. Hit apply. So we're done with our cell zone. We're going to open up the boundary conditions, select inlet, and from the problem statement, it gives us the input of a mass flow rate. So we're going to change the cold inlet. We'll right click, hover over type, and go to mass flow inlet. So now we can change our mass flow rate to 5 kilograms per second for the water. And in the thermal tab, from the problem statement, it's 10 degrees Celsius, which is 283 degree Kelvin. Make sure it's saved. We'll do the same for the hot inlet. Change the type to mass flow. Change the mass flow rate to 1. Thermal 383, which is 110 degrees Celsius from the problem statement. So now we're going to change the cold and hot outlet to an outflow by selecting and right clicking. And for the walls, we'll double click and open up, and we'll set in the thermal tab, we'll set all of the, select the material name to steel, which we created earlier, and the wall thickness to 5 millimeters. For the shell wall, we'll do the same thing. Change the material type to steel and the wall thickness to 5 millimeters. And make sure both of those saved. So now we're done with the boundary conditions, and we can open up the methods. You can change some different parameters here, but we're just going to leave these as is for now. So now we're going to go to monitors, click residual, and we're going to change all of these to 10 to the negative 5, and then hit OK. And now we're going to go to the initialization. Hybrid is more of a generic initialization, but we're going to use standard. We'll hit initialize, and you always have to initialize before you run the calculation. So now we're going to open up run calculation. We're going to set the number of iterations to 500. So when it's simulating, it'll basically do 500 calculations. Click calculate. And it'll look like this, and when all the values converge, there'll be a message pop up that says calculation complete. So now that our calculation is complete, we can go down to the bottom and open up reports. We'll click surface integrals. We'll change the report type to mass weighted average, and we want to know the temperature. And so for all of the inlets and outlets, you're going to have to select those surfaces. So we'll select cold inlet, cold outlet, hot inlet, and the hot outlet. And we'll hit compute. And down there at the bottom, you can see the individual temperatures for those boundary conditions. So the cold, the water, increased in temperature, and the steam on the inside decreased, but only by about 10. So we don't have a great heat exchanger, but just gives you an idea of how you can simulate these in ANSYS. So now we're going to solve for the optional part of the problem statement, which is to find the temperature contours of the heat exchanger. So we'll go to results, open up graphics, and select contours. We're going to deselect these surfaces and click new surface, and then select ISO surface. And so the surface of constant, we're going to change to mesh. We're going to create the X coordinate. We'll rename this the X plane. And then click create. We're going to do the same for the Y coordinate. Change the name to Y plane. And we'll do this a third time for the Z coordinate. To Z plane. We're going to close this out. And now in our surfaces, or the contours, will change to temperature. And in our surfaces, we'll select the X plane, the Y plane, and the Z plane that we just created. Click Save Display. And so now you can see a 2D planar image of the inside of the heat exchanger in the X, Y, and Z direction to get an idea of the heat transfer that's happening inside of the heat exchanger. We're starting a dark blue, which is the coldest on our graph to the left, going to a lighter blue, and you can see kind of the turbulent nature of the steam on the inside. And the heat transfer in the pipe wall.